Welcome to the 35th lecture. So, today we will see some more applications of reduction. So, last time towards the end we showed that as an example, we showed that the complement of ATM reduces to ETM. So, ETM is the language of all encodings of all Turing machines M whose language is empty, and by this, because we know that ATM complement is not Turing recognizable, this implies that ETM is not Turing recognizable. Okay. So, we are going to use a similar theme. So, to construct, so to show this reduction, we constructed a computable function f, which took as input an instance of ATM bar, which is a machine M and a string W, and it produced an instance of ETM, which is an encoding of some machine N, such that if M does not accept W, then the language of N is empty, and if M accepts W, then the language of N was not empty. So, that is what we showed last time. So, today we will see more examples as to how we can use reductions to prove languages are undecidable. So, the first language that we will choose is the language EQTM. So, EQTM consists of encodings of two machines M1 and M2 such that M1 and M2 are Turing machines and the language of M1 equals the language of M2. Okay. So, this is similar to the languages EQDFA and EQCFG that we had seen earlier, but in this case we will show that this is undecidable. Okay. So, how do we prove this? So, what we will show is that ETM reduces to EQTM. Okay. So, this is what we will show. So, we will construct a computable function f that will do the following. So, what does f do? So, first f takes as input a machine M, let us say. So, first what it will do is that it will construct a Turing machine N1 that rejects all inputs. Okay. So, in other words, the language of N1 is the empty language, and it will construct another Turing machine N2, which will just be the machine M1. Okay. So, I will write it as set N2 to be the machine M. Okay. And now it outputs the pair N1 comma N2. Okay. So, in our reduction, the reduction function f, what it does is that it takes a machine M and it sets N2 to be the same machine M. So, it just copies the encoding of M to N2, and for N1 it constructs a trivial machine that rejects all its input. So, the language of N1 is empty. Okay. So, now let us see why this is correct. So, proof of correctness. Okay. So, suppose M, the encoding of M belong to ETM. Okay. So, what does this imply? So, this implies that the language of M is empty. Now, this implies because N2 is nothing but, so N2 here is nothing but M. So, this implies that the language of N2 is also empty, and we had set the language of N1 to be empty, which implies that the language of N1 equals the language of N2, which implies that N1 comma N2 is in EQTM. Okay. Now, on the other hand, we have to show both directions. So, it should be, so observe that it should show for both, for instances which are in the language and instances which are outside the language. So, it is an if and only if condition. So, if M is not an element of ETM, then the language of M is non-empty, which implies because the language of N2 will also be not empty, therefore, it would imply that the language of N1, which is empty, is not equal to the language of N2, which implies that N1 comma N2 is not in EQTM. Okay. So, this completes our proof. Hence, we have that ETM reduces to EQTM. Okay. So, let us look at another simple example. So, consider a language, let us call it con TM. So, con stands for concatenate. So, it consists of encodings of 3 machines M1, M2 and M3. Okay. So, M1, M2 and M3 are 3 Turing machines, and the language of M1 is equal to the language of M2 concatenated with the language of N3, let us say. Okay. So, I am given 3 machines such that they have this particular property, and I want to prove that con TM is undecidable. Okay. So, what we will show is so now that we have proven EQTM is undecidable, we will show that EQTM reduces to con TM. Okay. So, how do we prove this? So, let us construct our reduction. So, we construct a function f, okay, that takes as input. Okay. So, what do we want to reduce? So, we want to reduce EQTM to con TM. So, our input should be an instance of EQTM. Okay. So, I take as input an instance of EQTM. So, an instance of EQTM is an encoding of 2 Turing machines. So, let us say I take the machine M1 and M2 as input, and what I want to output, let me write it down. is an instance of ConTM, which is an encoding of 3 Turing machines. So, I will have N1, N2 and N3. Okay. So, what do we do? So, first we set N1 as equal to M1. Okay, so, the machine N1 is nothing but the machine M1. Set N2 to be the machine M2. Okay, once again they are the same machine. And for M3 what we will do is that so design a Turing machine N3 that accepts only the string epsilon. Okay. So, N3 accepts only one string, which is epsilon. So, it checks what its input is. So, if its input is some non-empty string, it will reject. Only if its input is the empty string epsilon, it is going to accept, otherwise it will always reject. Okay. Now, let us see why our reduction works correctly. Okay. So, suppose M1 comma M2 is an instance of EQTM. What does that mean? So, it means that L of M1 equals L of M2. Okay. So, if L of M1 equals L of N2, okay, then what we have is that L of N1 equals L of N2, okay, because N1 is M1 and N2 is M2. Now, I use an identity from regular expression. Okay, so, remember that we had an identity that suppose if I have a language L. So, if I look at the concatenation of L with the empty string, okay, so if I concatenate L with the language which contains only the empty string, then I get the language L itself, okay, because the empty string concatenated with any string gives back the same string, hence I get the language L. So, this implies that this is nothing but L of N1, which is equal to L of N2 concatenated with only the string epsilon, but by my construction this is nothing but L of N1 equals L of N2 concatenated with L of N3, because that is how I designed N3 to contain only the empty string. Okay. Now, so this proves that N1, N2, N3 is contained in ConTM. On the other hand, if L M1 is not equal to L M2, then L of N1 is not equal to L of N2, which implies that L of N1 is not equal to L of N2 concatenated with L of N3, which is nothing but the empty string. So, L of N3 concatenated with L of N2 is just L of N2. Okay. So, therefore, we have this. Okay. So, this proves that EQTM reduces to con Tm, therefore con Tm is undecidable. Okay. So, now let us look at the last example of today. So, now we will look at a slightly more non-trivial example. It is a little bit more involved than the first two examples. Okay. So, suppose let us define this language reg Tm as encodings of Turing machines M. So, M is a Turing machine and the language of M is regular. Okay. So, a language of a Turing machine can be anything. I mean, it can also be a non-regular language, but let us say that of course, I can have Turing machines, for example, which accept the empty set, or Turing machine that accepts sigma star or some other regular language. So, I do have certain Turing machines that accept regular languages. So, consider the class or consider the language of encodings of all those Turing machines whose language is regular. Okay. So, what we will prove is that ATM complement reduces to regTM, okay. And this would show that regTM is undecidable. In particular, it is not even Turing recognizable. Okay. So, once again we need to design a computable function f. So, what is an instance? So, an instance of ATM bar will be a pair of the following m comma w, and an instance of regTM is a single machine, let us say n. Okay. So, given m comma w, I want to map it to a machine n such that if m does not accept w, then this guy is regular, and if n accepts w, then this guy is not regular. So, what is our reduction going to be? So, we take as input a machine m comma w. Okay. So, what we do now is that we construct a machine, or let me write as Turing machine. So, construct a Turing machine n that on input x does the following. Okay. So, what does n do? So, n of course has m, a copy of m and w hard coded in it. Okay. So, n simulates m on w. Okay. So, n has a copy of m and w hard coded in it. So, it simulates m on w if m rejects, then reject. Okay. So, what the machine n does is, if m rejects x w, then it rejects. If m rejects w, then reject. Otherwise, else check if x is of the form 0 to the power n 1 to the power n. Okay. And so let me continue here. If so, then accept, else reject. Okay. So, what are we doing essentially? So, let us go through it. First I simulate m on w. So, they are hard coded into the description of n. So, what the machine n does at the beginning is it simulates m on w. If it loops forever, then of course n will also loop forever, it will never stop. Otherwise, it checks the answer. So, if m rejects w, then n will immediately reject. Else, so if m accepts w, it checks whether the input of n, okay, so the input of n was x. So, it checks whether x is of the form 0 to the power n 1 to the power n. Okay. So, why do we take this? So, we take a string of the form 0 to the power n 1 to the power n, because we know that this is, so strings of this form give us a non-regular language. Okay. So, that is the first non-regular language that we saw. So, that is why we check if the string has this particular form. If it has this particular form, okay, then we accept, else reject. Okay. And our output is the machine n. Okay. So, if I want to give a box, a diagrammatic picture of what is happening. So, this is my reduction f. So, what is the reduction doing? It is taking two things as input. It takes a machine m and it takes a string w, and it outputs another machine n. Now, how does it define n? So, this machine n is defined as follows. So, this is the machine n. It takes as input x. Okay. So, first it simulates m on w. So, if m rejects w, then reject, else check if x is of the form 0 to the power n 1 to the power n. If yes, then it accepts, else it rejects. Okay. So, it is rejecting in these two cases, it is accepting here. So, this is the design of the machine, and f finally outputs the machine. Okay. So, now let us try to analyze the proof of correctness of this reduction. So, suppose m comma w does not belong to ATM, okay, or in other words, let us say that m comma w belongs to ATM bar. Okay. So, this means that m does not accept w. So, if m does not accept w, two things can happen. In the first step, either it loops on w forever, in which case I do not even go to the second step, or it rejects w, in which case the machine n rejects x. Okay. So, in either two cases the machine n observe that it does not accept any x. So, all x's are either getting rejected or the machine n loops forever on x. So, this implies that the language of n is the empty set, which implies that the language of n is regular, because the empty set is a regular language, which implies that n belongs to regdm. Okay. On the other hand, if m comma w does not belong to ATM bar, it means that m accepts w. Okay. So, in this case what happens? So, if m accepts w, then we go to step 3, we check if x has this form, if x is of the form 0 to the power n, 1 to the power n. If so, then we accept, else we reject. Okay. So, what will be the language of n in this case? So, the language of n in this case is going to be all strings which have the form 0 to the power n, 1 to the power n. Okay. So, in this case the language of n is set of all strings of the form 0 to the power n, 1 to the power n for n greater than or equal to 0. Okay. So, this implies that the language of n, and we know that this is a non-regular language. So, the language of n is not regular, which implies that n does not belong to regdm. Okay. So, this completes our proof. Okay. So, now similar idea can also be used to show that CFL-TM is undecidable. So, CFL-TM consists of encodings of all Turing machines whose language is a CFL or a context free language. Okay. So, in a similar manner I can construct a language of strings which is not a context free language, and on the other hand let us say I construct a context free language, let us say the empty language, and we will be done. So, what we will see next time in our next lecture is a generalization of this technique. Okay. So, a generalization is known as Rice's theorem. So, in our next lecture we will first understand how to define a generalization of this theme. We will look at the statement of Rice's theorem, and then we will see how to prove it. Thank you.